Hello everyone. Today we will discuss RAG with PGVector. In this lecture we will cover what Retrieval Augmented Generation RAG is, why most RAG systems fail in production, how PGVector works as a vector database, the architecture of a fully serverless AWS RAG system, vector database design, the end-to-end RAG pipeline, production readiness requirements, and how to scale to millions of documents. Production-ready RAG using PGVector on AWS. Modern AI systems require retrieval and reasoning, not just LLM prompting. Retrieval Augmented Generation RAG combines the power of semantic search with large language models to provide accurate, contextual responses grounded in your data. This architecture uses PGVector for vector storage, AWS Lambda for orchestration, and Amazon Bedrock for LLM inference. AI systems are pipelines, not just models, and understanding this is crucial for building production systems. Why most RAG systems fail in production? Most RAG systems fail because they are built as prototypes rather than production systems. Common failures include hard-coded prompts with no versioning, no governance, no multi-tenant isolation, expensive external vector databases, and no monitoring. They also lack cost control mechanisms, prompt management, and observability. Production RAG requires tenant isolation for SaaS applications, monitoring for debugging, and governance for compliance. Without these, systems break under real-world load and security requirements. What RAG actually is? RAG is a pipeline that connects retrieval with generation. First, the user query is converted into an embedding. Then vector similarity search retrieves the most relevant documents using PGVector. These documents are assembled as context. The LLM then reasons over this context and generates a structured response. Key components include embeddings, vector search, context assembly, LLM reasoning, structured output, and grounding in real data. RAG combines retrieval and reasoning, where retrieval provides facts and the LLM provides understanding and synthesis. Why PGVector instead of external vector DB? PGVector enables vector search directly inside PostgreSQL. Traditional architectures use external vector databases like Pinecone or Weaviate along with a separate SQL database. PGVector simplifies this into a single system. Advantages include lower infrastructure cost, simpler architecture, SQL-native vector search, built-in multi-tenant filtering, easier backups and replication, ACID transactions, and familiar tooling. This makes it ideal for production SaaS systems where simplicity and reliability are important. AWS Production Architecture. The architecture is fully serverless and event-driven. API Gateway handles user requests. AWS Lambda orchestrates the RAG pipeline, including embedding generation, vector retrieval, prompt assembly, and LLM inference. Amazon Bedrock provides access to Claude. RDS PostgreSQL with PGVector stores embeddings and documents. CloudWatch handles monitoring and logging. This design scales automatically, supports high concurrency, and minimizes operational overhead. Vector database design. The documents table contains an ID, tenant ID, content, embedding vector, metadata, and timestamp. The tenant ID ensures multi-tenant isolation. Metadata is stored in JSON-B. The embedding column uses a 1536-dimensional vector. Indexes include an HNSW index for vector search and a B-tree index on tenant ID. This design ensures performance, security, and flexibility while supporting production workloads. Vector similarity search works by converting the query into an embedding and comparing it against stored vectors using cosine distance. The system always filters by tenant ID for security and performance. It retrieves the top K results, typically 5 to 10, to balance relevance and cost. The HNSW index enables fast approximate nearest neighbor search, and additional metadata filters can refine results. The RAG pipeline consists of multiple stages. First, the user query is processed and validated. Then embeddings are generated using OpenAI models. Next, PGVector retrieves the most relevant documents. These are used to assemble context. A prompt is constructed and passed to Claude via Amazon Bedrock. The model generates a response, which is then formatted into structured JSON. The total pipeline typically takes around 2.2 seconds, with most latency coming from LLM inference. Production systems require strong operational controls. This includes monitoring for latency, errors, and token usage. Logging is handled through CloudWatch. Security features include tenant isolation, input validation, and rate limiting. Governance includes prompt versioning, audit logging, and access control. Cost control mechanisms, alerting systems, and rollback strategies are also essential. Without these, systems cannot operate reliably at scale. Scaling requires multiple optimization strategies. HNSW indexing enables efficient vector search. Query caching improves performance for repeated queries. Table partitioning by tenant improves query isolation and performance. Async embedding generation separates ingestion from processing. A re-ranking layer improves accuracy of results. Red replicas distribute query load, and connection pooling prevents database overload. Together, these techniques enable systems that handle millions of documents and thousands of concurrent users. Conclusion: RAG is not just a model-based approach, but a complete system architecture. PGVector simplifies vector storage by integrating it into PostgreSQL. AWS serverless services enable scalability and reliability. Production systems require governance, monitoring, and cost control. AI systems are pipelines, not just models, and understanding this is key to building production-ready RAG systems. Thank you for watching.